visiting with us. Oh, thank you very much for getting that, Tracy. All right, let's go ahead and get started. We appreciate Jessica Iriarte joining us. She's a senior manager of data science at Vroom, an e-commerce company that enables customers to buy, sell, and finance cars online. Before Vroom, Jessica launched and grew a data science team at Well Data Labs, serving as a subject matter expert to bridge the technical gap between engineers and data scientists. She led the development of robust models for time series sensor data, work that results in several patent pending technologies. She holds a BS and MS degrees in petroleum engineering and has over 10 years of experience in data science research completions. Jessica served as the SBE Denver chairperson, received the 2018 Denver Business Journal Top Woman in Energy Award, and the 2020 SBE Young Member Outstanding Service Award. Jessica, thank you very much for joining us today. The floor is now yours.
Thank you so much, Dr. Birch, for having me and everyone today attending. Appreciate you all taking the time. You're in your busy schedules, especially jumping around between classes. So thank you so much. Before we get started, I would like to thank the SBE Foundation, Offshore Europe, and AIME for supporting the Distinguished Lecturer Program. I would also like to thank my managers at Vroom for allowing me to participate on this program. And last but certainly not least, the SBE Distinguished Lecturer staff, who are amazing and do a lot of hard work in the background to make all of these programs a success. Again, it's truly an honor to be here. I'll go ahead and introduce my talk. Let's see. All right, the title of this talk is Data Science Applications to Time Series Data, a hydraulic fracturing case study. So I will basically, it's really focused on how organizations can successfully plan and implement a data science program. I focus on, actually, let's walk through our outline. I will focus on some overview of data science, very basic, high level overview. Then I like to talk about the workflow that I like to apply when implementing data science. What is the process that we should follow? And then I will have 3 case studies for today, showcasing how the different applications for data science for time series data focus on hydraulic fracturing data. However, it's very much applicable to other continuous data sets like time series or depth series data. And I will finalize with some takeaways. So data science continues to evolve as one of the most promising in-demand career paths for skilled professionals. For those who may not be familiar with what data science is or how does it even come to place, I'm sure a lot of you are familiar with a lot of these streaming services like Netflix or Hulu, or any of those are out there, where basically you're browsing around and it starts recommending you new shows or movies to watch. So these algorithms that are in the background of these softwares or these applications are basically recommendation systems built with machine learning. So basically, I will try to relate to this diagram that I have here, Venn diagram, where you basically have your data, which is data that you're collecting from hourly shows, streaming views, what time of the day users are logging in to watch, what kind of shows are more popular, and then features, for example, what actors are in those shows, what kind of theme are there, what location are users watching this from or streaming this from, and then algorithms. So basically a classifier or a clustering algorithm that by association tries to look at this data and features and then find common themes within these different shows and tell you, because you watch this, other people that watch that show also watch this show, or because you have watched this sort of theme, these are similar shows that align on those themes. So basically using these algorithms and statistical models to extract information and insights from data and relying on those patterns to sort of learn. And feature engineering and this concept I use especially specifically for the applications in oil and gas is that process of not only taking the important features from the data, but also creating new features, or you can call it new columns or new data points, to help improve the algorithm's performance, kind of help or enhance. Most of the data science applications in oil and gas today are based on automating manual tasks, such as classifying wells into different production conditions, like this predictive maintenance for rod pumps, dynamometer records, or finding the logs, predicting the logs, or not necessarily predicting, but maybe identifying deformation tops in logs, or maybe identifying what kind of operation is happening in real time or post-job in a rig operation, whether they're rotating or sighting, to be able to use it for diagnostics and optimization of the operations. And even though these data sets are coming from very different data sources and maybe coming in different formats, the similarity is that they are continuous data sets, whether they are time-based or depth-based, they are continuous, and these are really perfect candidates for applications of pattern recognition and predictions. Now, when we look at the potential, and again, when I mention about the applications, those are what we mostly see. We do see predictions, and we do see other different, more complex applications. And I think the industry is slowly moving there. But I see the future of having real-time predictions that can help us be more efficient, save money, produce more. And maybe we have this predictive integrated models that help us evaluate candidates within a field, where we take that data that comes from all the wells that we have operated in the field, understand or add some context to that data with feature engineering, understanding the unique asset level implications of the design and operation decisions made in each of those wells, and potentially, having this integrated model that can help us identify, those similar characteristics in new wells. And maybe having a model that help us, or a combination of models help us identify, what wells are going to need artificial lift in the next few years, or well stimulation, or which ones are going to be good candidates in the next 10 years for IOR, EOR. Now, the reality is that most of data science projects don't end up in production and don't end up being utilized by an end user. By production, I mean in the sense of how technology of software it's looked at, not necessarily as oil and gas is looked at. So, and this is not only a unique challenge within the industry, it's across industries. And what I would say identify that are, the challenges that I see the most, or the things that we can still, the opportunities that for us to work on in the industry are the lack of business support, because there's still a lot of misunderstanding on what data science is and what the applications are. There is lack of guidance and clear goals, and lack of connection. So that results in failed solutions. Isolated data science teams, similar theme. There is lack of collaborations between different departments, isolated data science teams that are treated more as an IT department or as a consultant team inside the company that is not necessarily integrated with the geoscientists or engineering departments. And then poor and silo data, which I'm sure you'll have heard a lot of talks talking about this specific challenge. So as the oil and gas industry continues to become more and more data intensive, and in-house data science teams become the norm, these are some of the considerations that we need to take into account when we are starting to implement these applications. So what is the data or the field data gathering process today? And I'll walk through what I've seen, at least in the hydraulic fracturing side, which tends to be a very manual process overall. So we generate, the service company or whoever is performing this job is generating the data, usually 1 second, or if it's that data is 1 foot or 10 feet. data that is produced per stage or per well, usually in a CSV or LAS file. Then you usually have a field engineer or a field supervisor that is collecting some of these important data points, summary stats, into a spreadsheet, or it turns into a PDF report a lot of the times. Sometimes you then have an on-site consultant that also manually enters these data points or their specific data points that they care about into their own database. Then you have an IT department that is collecting different data sets from different sources and potentially providing or administering a third-party database system. And you finally have the consumer, who are the ops team, who are manually sometimes normalizing this data to be able to do analysis or modeling. And then finally, using either some modeling, commercial software modeling techniques, or some visualization tools to be able to analyze this data. So overall, it's a very manual, intensive, and very resource intensive workflow that we see today. And throughout this process, we have different files created with different naming conventions, different units. So it has definitely been a challenge in the industry to move towards standardization. Then there is the issue of access to data, and that is also a struggle. And I'm sure as students and as faculty, that is something that sometimes is really hard to get a hold on. I have to say, North America has been a lead on public databases, and while granted, this is data that is self-reported, a lot of the times it's not the most clean or it's not the most trustworthy, but it does give us a place to start. For those who work directly with national companies or at a national oil company, they have their own proprietary databases with history of years and decades of data. And I do see times changing a little bit. I've seen like Equinor disclose all the subsurface and production data from a field in the Norwegian continental shelf. And I actually was able to find a lot of different databases, public databases that are international. So that's very encouraging to see that not only the US is moving towards that phase. Now moving into more of a workflow though. Because the applications for oil and gas, for automation in oil and gas are boundless, but sometimes finding where to start can be a little daunting. I like to think of or use the Agile approach rather than the waterfall approach, where we build minimum solutions or minimum viable products using this feedback loop of build, measure, and learn. Because one common misconception when it comes to building a new model, especially a data science or a machine learning model, is that it's going to be this magical thing that is going to solve a whole target business problem all at once. And that's not only unrealistic, but also this type of development tends to produce overly complicated models with long review and long project evaluation cycles. So to focus on adding business value today, me and my team have been successfully applying the lean methodology approach, where it's a core component of the lean startup methodology, which is actually adapted from the lean manufacturing from production systems from Toyota. So we're basically, the best practice is to break down problems, large problems, into small problems or small tasks, and then start small and then build upon and iterate on that. And that's why we show this as a cycle, basically, and not just like a more traditional project workflow where you have a start and end. This is more like it's always building and building. So how do I apply that, or how do we apply that to data science or a model development workflow? How to translate that? I always like to start with a discovery phase, or what I like to call it ideating or discovery phase. So where you try to understand what is the problem you're trying to solve. A lot of times we tackle business problems right away, thinking about a solution and evaluating solutions without trying to first take a step back and understanding what is the real challenge and problem that we have. And then thinking from that, how do we solve it? It may seem very obvious, but a lot of the times we're right away jumping into different solutions and evaluating which one is best without really understanding, interviewing, who is your end user, whether that end user will be a geologist or a reservoir engineer or a drilling engineer, understanding what is the challenge they have today, then trying to collect some data and do some exploratory analysis, understanding what is the state of the data, how much you have, and how much of it really you can use to build a model. Then start building an approach of a solution, and that might be 1 or 2 or 3 approaches. And that is one thing that is key in data science. There is a lot of experimentation. So sometimes you might try 1 or 2 approaches and see which model it's giving you a better fit for the type of predictions that you're looking for. And then you usually have some sort of set up aside validation and testing data that you use to validate your model. You might spend some time here experimenting around until you come up with a minimum solution, again, that adds value today. It doesn't have to be perfect. It doesn't have to solve it all, but it provides some value today and enough value that you can get feedback and continue to improve your performance of your model. Then it's always really important to document your trials, your code, and then deploy it, whether that is as complicated as deploying it in a commercial or proprietary software, or as simple as delivering a macro or a spreadsheet or a report. But basically having something that you can deliver to the end user so you can collect some unbiased feedback from them. And then once you collect all of that feedback and learn from what was the model doing well and not doing well, then go back to the drawing board and iterate on that version of the model. Something that's really important throughout this process, especially within the oil and gas industry, where the data is so technical and so related to physical behaviors and not just seasonality or other types of effects that happens in other types of data sets. It is really important to keep that connection with the subject matter experts. And that's why I have this science of SMEs all over the process. When you are discovering, when you are trying to understand the problem, when you are measuring or validating your model, when you deliver it, and when you iterate, all of this is really important to keep in contact with your subject matter experts, because they will help you add context to the data, understand whether the model is predicting something that makes sense in real life and it relates to the actual physical behavior that is happening on the ground or in the surface. And then the other thing that I think is really important that sometimes we think it's obvious, but sometimes get overlooked, is bias in the models. If you decide to start really small and your first version of the model is going to cover, say, operations within your well or your field or your pad, and there is specific, for example, chalk reservoirs in the North Sea, and then you try to immediately use that model for, say, using data from oil sands from Canada or unconventional reservoirs from anywhere in North America, then the model might be so biased to the specific data that you show that clearly is not going to perform well when using other data sets. So that's a really good way of first thinking about bias, but also thinking about ways to increase complexity in your modeling. So you can start small with one type of reservoir and then add different types as you go. Sort of think of it like layers in an onion. So now we'll move into the case studies. And before that, I always like to do a very simple and quick introduction, maybe too simplified for some, of hydraulic fracturing in horizontal wells. I'm sure all of you are even more experts than I am on this topic, but I always like to show this cartoon, which is not a realistic representation. Again, it's just a cartoon of how the hydraulic fracturing process works. So if you were to look at a well from top view, you have your casing, your perforations, you have your formation, and then you start pumping your water and propellant and create a fracture. And this is sort of a cartoon representation of that water leaking out through the formation and that fracture closing. When you are looking at a horizontal well, for that, you are splitting the well, say, into steps or into sections. And these sections are called stages. And then as you go, the most common technique for this is plug and perf, where you run your perforations, pump your fracture, and then plug it, which I don't have it included here, but let's say there's an X here, you plug it to isolate, and then you move along the ladder to complete all your different stages. So throughout each of these stages, usually each of those jobs take about 1.5 to 2 hours, depending on many factors. And then each of these 1 to 2 hour jobs generates a CSV file or LAS file, where you're collecting data second by second. Again, very simplistic cartoon representation. Fractures don't necessarily look like this. And this is a typical fracture treatment plot of one of those stages. How does that look like in data? And this is how it is, where you have your data channels, in this case, pressure in red, rate in blue, and propellant concentration in green, where the x-axis is your time and the y-axis is the values for each of those data channels. And you can immediately start to see different patterns and different changes throughout the job. So now we talk about data collection. I didn't necessarily mention a lot of data consistency, but data consistency is really important, or data quality, especially when you're trying to make predictions based on this data. Something that might be overlooked is, as I mentioned before, throughout the process where you're collecting data, a lot of the times you're not going to use all of these files that are huge. Sometimes you just use the summary stats, like what was my average pressure, what was my average rate, what was the total volumes pumped per stage, and then you use that. You might be having, that might be enough of a resolution for you to use. However, it is really important how those averages and totals were calculated, because usually you use different boundaries, or in the field, I've seen it, that different crews, different service companies choose different boundaries. So I'm going to use this example where you have a day crew that chooses this start and this end of end time for designating the boundaries of this stage. And then you have the night crew that decides to say, well, until I don't have enough rate, I don't use my start. I don't consider that was started and ended. So we have completely different boundary conditions to use to calculate this averages and summary stats. So even something as simple as designating when the job started and ended, it is really important, and it is the baseline for having data consistency. So that is a very low-hanging fruit for using automation and machine learning, because you can use that to automatically recognize those and trust that most of the time, 90%, depending on the accuracy you get or the performance of this model, it's going to get it consistently. So at least you know that you don't have to worry about whether you have different crews or different service companies in the field. So for my first case study, I like to talk about ISIP, or instantaneous shutting pressure. This is one of the most common events labeled in hydraulic fracturing data. And that's why I always like to show it, because most people who are familiar with this data will be familiar with this data point. Usually in the field, again, this is a fracture treatment plot, a sample of it. When you're trying to find the ISIP, you would usually focus on the end when the pumps had shut down, and you can see the rate, which is again in blue, shutting down, going down to 0, and then the pressure creating this water hammer effect until it kind of stabilizes and starts to fall off as the pressure is leaking off. So the ISIP is that intersection between, if you were to trace back that pressure fall off back to the point where the rate is 0. So that is the ISIP. And very similar to that step-by-step process that I just explained, we decided to build our model. It wasn't straightforward, to be honest. We started with different things. We started with like, oh, the model, we know how to recognize an ISIP. And then we realized that wasn't realistic. So then we broke it down into a couple of different steps. We also use a lot of different examples of different water-hammer effects and different ISIP behaviors and values. So we actually, when we talk about the minimum solution, we started with the most straightforward, which was the simplest for us to visually identify. And then as we wanted the model to be more and more robust, we added more different stages that behave very differently. So that is also another approach of how to build complexity within your model. So at the end, we use around 870 stages from basins all over North America. And we train a neural network to identify and isolate that area, which I mentioned before. And then we use a linear regression to find that point, that cross point that we're looking for. So the way we actually use the neural network was as a classifier, where we're using it as a binary classification problem, where we say everything that is a 1, we want to keep, everything that is a 0, we don't need right now. So that's how we go from a whole stage of data to the section that we are interested in. The model clearly is not perfect at filtering that out. So it will sometimes get some areas from shutting down, and then at the end, when the pressure is bleed off, when the valve in the surface is open. So what will happen is that then the straight fit or that linear regression wasn't very accurate. It will be very outweighed by these data points. So we apply some standard deviation filters using the median distribution with these data points, which are mainly concentrated in these points here of the pressure fall-off. And once we remove those, then we get a better fit for our linear regression and a closer to what we will manually pick ISIP value. Now, when evaluating a model, we always use the term accuracy as a kind of catch-all. However, accuracy has a specific definition within machine learning or within data science validation. So for this specific model, we use a different metric, and that is really always important to evaluate. Like, what does success look like for your model or for your prediction, and how do you measure that? For us, for example, the model was really good at filtering it down, and it might be 99.99% predicting that, but that didn't really mean anything to us, because when it comes to how unbalanced those predictions are, it makes sense that it looks so good on percentage. So the way we measure it was comparing what we mattered to us, which was the ISIP value, the pressure value that we were predicting. And if we were manually picking that value, what would that pressure value be, and how far within seconds we were from what we were manually be. Actually, let me clarify that. We didn't use the time difference for ISIP. We used that for the start and end time. For here, we only used the pressure, which is what mattered to us. So what we did is, on our validation data set, we had, on our test bed data set, we had some stages that some fracturing completions engineers manually picked. And then we compared the difference, the delta, between what was manually versus what was predicted. And then I'm graphing here, or I'm showing here in this plot, those differences. You will see that they're color coded from 0 to 1,000 and something. And you will see that most of these predictions were less than 100 PSI difference from the manually peaked value. So when we looked at that, when a median difference of 35 PSI, which for those who are not familiar with ISIP values, it's usually they are in the 1,000. Not usually, most of the time they are in the 1,000. I would say mostly between 4,000 or 5,000. So 35 PSI difference is very minimal. So for next case study, I'm going to talk about well pressure monitoring, which is being very popular these days, especially in North America. So for those who are not familiar, this is, as new wells are drilled or completed in a pad, existing wells can be affected by a pressure interference or communication from the fractures created in the wells. So the FDIs or fracture-driven interactions can be observed in this when you're monitoring the pressure of those existing wells, or also called parent wells or legacy wells, primary wells. They have a lot of different names. And you can see them there in this graph. For example, I have these 4 active wells, which you will see they will behave very similar. They go up and then down. And those are the active fracturings from different wells. You can see they're going 1, 1, 1, 1, and then they go back to the first. That's kind of the sequence they were fracturing them. And then for the monitoring wells, you have the lower pressures here that are kind of tend to be declining throughout time until you got that FDI or fracture-driven interaction with the pressure increases. So we're trying, when we see that inflection point, we can see there is a communication between those 2 wells to that active well. And this is really a great application of data science or the automation, because when you're handling this large amount of data that are coming from potentially different paths, different operations, it becomes a little challenging to be able to monitor all of these at once and be able to look at every single data point that is changing. And also something that is sometimes overlooked is visualizing the data right away. So that's the first thing for me, especially when handling so much data, to first look at it, kind of skim it, do some exploratory visualizations to see where to focus first. So unlike the first model, this was a very a simpler approach, where we're basically trying to identify these pressure changes. And the way we do that is we're trying to help the model identify them easier. So the way we do that is using feature engineering, so creating these new features or new columns, which are basically derivatives of the pressure. So what we're trying to do is like exaggerate that behavior of the pressure change and help the model know, hey, this exaggerated behavior is what we're looking for, because especially sometimes with monitoring well, those pressure changes are very subtle. So it does help a lot to use those extra aids or features. And why is this important, or how can we even use this? Well, I think this is like one of the simplest yet more powerful uses of automation, because it provides these actionable insights, especially when you want to choose an active well defense strategy, and if you want to do it in real time. So in this case, the operator, for example, identified that pressure change early in the job and decided we're going to pump a load rate injection, semi-continuous treating water into that legacy well to create that pressure wall or pressure protection and mitigate the effect of that factor-driven interaction. So this is, again, a really great way to leverage that real-time monitoring pressure and injection on legacy wells, and not only determining when they're happening, but also which wells you want to protect, and deciding at what moment you need to protect them. Because might be that you're fracturing this blue well and you're getting interactions in the yellow well, but then maybe you're fracturing the red well and you get interactions in the gray well. So then maybe when you're fracturing this, you don't need to protect the other well, but this is the one you want to focus on. So it's really helpful to strategizing on your well defense strategy. For my last case study, we did a pump schedule recognition. And this is really a great example of how to break down a big problem into smaller ones. And we're basically, instead of saying, hey, this is our pump schedule recipe. And for those not familiar, pump schedules are basically like a recipe that the pumper uses to decide what step to follow to pump the job. However, it's almost never the same as planned because of operations. So a lot of the times engineers want to compare what they design versus what they actually pumped. So instead of saying, this is all this data, this is the POM schedule, how it looks like, train a model that automatically recognizes it, we broke down the entire procedure into various models. So first one that identified the start and end time of the stage, then one that identifies the problem related channels, so the changes within the problem channel, which are the ISID and the problem, and then divide the problem ramps into problem steps, and then basically use all of these flags as boundaries to create summary stats for all of this. For this model, we actually use around 577 stages from all major North American basins. And then we calibrated it with about 112 stages and tested it with about 465 stages. So something that I haven't mentioned before is the use of data pre-processing in some signal processing, some basic signal processing techniques that we use for before training these models. Because a lot of this data is sensor data, it is very noisy. And especially when you have high resolution sensors that are measuring 0.1, 0.2 PSI changes or rate changes or whatever you're measuring. And then because, again, they're just sensor data, it comes really noisy. So here's one example of the problem concentration channel and how it looks really, really noisy. You can still see sort of that staircase behavior that you would expect, very noisy. So we apply a medium filter, which help us filter down the noise without smoothing it too much, that it removes the edges. We do want to keep the edges of these little stair steps. So that's why we decided, you can see here a cartoon representation between a medium filter and a simple smooth. Usually smoothing tends to round and create that rounding visual that you will look into these data. However, the great thing about this moving median filter is that it does reduce the magnitude of those outliers without, and flattening the signal without losing the edges that we wanted to keep. So after we do that, for us to identify, usually you have one ramp of problem, but in this case, there were several ones, and we want to model that because we wanted our models to be robust for a lot of different data sources from all over the country, where fracs look very different. So what we do here is the model linearly normalizes that smooth problem concentration channel that we created. And then basically it creates this new channel that lies between 0 and 1. And this creates this set of buckets that are using the floor function. So it's rounding down to the nearest integer, where basically it creates this sort of binary signal of zeros and ones, where one is this, there is, we're pumping propellant right now, and 0 is we're not pumping propellant. And then we use the first order differencing to basically identify them, like the start and end of each of those buckets. Where basically when it changes from 0 to 1 or a positive change is the start, and then when it changes from 1 to 0 or is a negative change, then it's the end of that block of that bucket. So one thing I haven't mentioned so far is that the problem concentration channel, for those who are not familiar, is calculated from the slurry density readings, which are provided by a densometer, which is placed in the line. So basically what it's doing is reading the baseline density of the fluid that is going through the pipe. And usually the base fluid is water. So the baseline is going to be the density of water. So every time it changes, it means it's no longer just water. And usually it's going to go up as the density, as you're adding more and more propellant, and the density of the whole slurry is changing. One thing that is interesting is that acid also has a different density than water. So we usually see it in the in the propellant concentration channel. However, we see it almost as a spike at the beginning. So we see that this little spike here is actually not propellant, but acid. So for us to be able to split it from this is the acid and these are the propellant, we basically take the summary statistics from each of these buckets, and then separated by duration. And by summary stats, this looks like an acid and this looks like propant. Now we have acid, we have propant. Now we want to further split the propant into steps, and each of these are steps basically. And for this, we use recursive partitioning or decision tree analysis, basically, where we're basically grouping the data by each of these steps. So it's very similar to how you will feed, a piecewise constant fit into this data, kind of like how we look with a straight fit, but instead of being a diagonal fit, you're feeding to each of these steps. And at the end, what you get is this sort of flow chart that basically the end nodes represent each of those steps. So I'm highlighting this final step that says the value for it, it's 0.5, which is the 0.5 propant concentration for this specific step. So basically, we're using this decision tree to split out each of these and like group each of these steps. And then we find the summary stats for each of those. So finally, we have basically identified each of these different boundaries or different steps that are considered within that recipe that you're following and during the pump schedule. And then we're able to take that and create that table where we have all of those statistics of average pressure, volumes, concentrations. And the model was actually really accurate by layering this way, but breaking it down by using signal processing techniques. And it was able to recognize almost 96% of the label flags. And then 95% of those predictions were within 3 seconds. And then 97.5 were within 1 minute, which is a really good accuracy for what we're looking at here. Again, looking at metrics that matter to us and not necessarily what the traditional definition of accuracy will look at. So to finalize my talk, I like to just summarize that really the goal here with the application of these techniques and with data science and with automation is to empower engineers to focus on the analytics and enhance that critical decision making, especially when either looking at large data sets that almost nobody on their own has time to look at by themselves, but also that helps with making decisions in real time when you have large operations that are concurrent. What my takeaway or the important takeaway that I want you to walk away from here with is the process, which is first understand the problem. It's really important to always start from that. So start from that, brainstorm, discover, interview experts, then narrow the focus. Try not to boil the ocean at once, just to begin with. Try to narrow it to a small solution and then build that feedback loop, break the silos with other departments, get feedback, learn from that, iterate. And obviously throughout that, it's important to get leadership support. So to finalize, just a reminder that your feedback is important. So please enter spe.org/DL and send an evaluation from this talk. Thank you.
Jessica, thank you very much. We appreciate your talk today. Now, what I want to do is I want to first of all give an opportunity to our students, graduate, undergraduate students. If anyone would like to ask a question, go ahead, just unmute. Julian, I see a hand up. Do you want to go ahead and ask?
Yes. First, thank you so much for the presentation. I really like it. Regarding your presentation on slide 19, the first case study, how can you avoid too much bias when manually picking the shedding pressure? In addition, for example, analyzing overfitting. And I think this also leads to another question. What threshold divides valuable, useful expert knowledge with bias that could impair the decisions? So what's the threshold to say this is knowledge actually is helping the model or actually is not at all? Thank you.
That's a great question. Okay, how to avoid bias. So we had 3 completions engineers picking it manually, and we have a very specific process to use, which was the FECET, kind of industry approved method, which was the one that I explained. So yes, there is always going to be bias. So we tried to balance it out by having different engineers, and then we kind of averaged the values. They were very, very close, actually. The threshold between useful and bias, that's a really important point, because when we add too much expertise or too much context, it gets really biased to that one person. And that's why I think it's so important to interview more than one person, take their feedback, and not just have the expertise of one person. And then there are always unexpected things that you didn't consider that affect bias for the model. For example, for ISIP, we had chosen a bunch of different stages from different fields. We didn't realize that most of the values lie between 5,000 or 6,000 and 8,000. So when we started to test it with values like the ISIP would have been 2,000 or 9,000, the model was like out of it. And we never thought that would be an issue. So then we had to add more stages to add more diversity and like more ranges. So we didn't realize the model was also learning that the values should lay between that range. And that was sort of unexpected. So that is a really good point. I think is more what you're making there. Is just really important for all of us to keep honest to each other and to keep checking our biases and get more and more feedback on the model on not the same person, but different users. And test it with a lot of different data, because the more you test it with different data, the more you find all of these different biases that you didn't even realize the model had.
Thank you so much. I appreciate it.
Thank you, Julian. Other questions from students? Anyone? All right, what we'll do is we'll open, oh, sorry, Jessica.
You can also type it in the chat if you feel shy to speak up. Feel free to do that.
Awesome, thank you for that. What we'll do is we'll open it up to everyone, faculty and students. Any questions? Jessica, I have a question while people are thinking right now. What I find is that with machine learning, there's a focus on accuracy. In the estimates, accurate estimates of a phenomenon, the response feature, they would say. What about uncertainty? I think we're really good at uncertainty in the subsurface. I want to ask you for your impressions as far as where we are as far as modeling uncertainty with these data science methods.
Yeah. That's a really good question. You can always focus it on that. So my team now actually focus more on error and finding how much we have the error versus how good we're doing. And then obviously that also helps with modeling as the data drifts, and that happened basically with what happened with ISIP. We trained it with specific data that we had. And then as the data we were collecting started to drift because operation changes and because we started to factor different formations and the data changes, your model is no longer predicting as you train it because again, it's biased. So it's really important to kind of monitor that error or that uncertainty. I think it's also, again, understanding what is the capability of the model and staying honest on what is there to do and what is not there to do. And it's not necessarily then to get perfection. Yeah, especially with real-time predictions.
Yeah, and we definitely, I think we often drive ourselves to overfit.
Oh yeah.
Try to do too much. Any other questions? All right, Jessica, we appreciate you visiting. As I said at the beginning of the talk, we have an IOU for a visit to Austin and to be here in Texas with us. We do appreciate you visiting us and joining us remotely. Thank you for taking the time today.
Thank you so much for having me and for your questions, for listening. Feel free to contact me on LinkedIn if you have any other questions. And yeah, I would love to eventually come in person and meet you all.
All right, thank you very much.
Thank you.